Okay, so now we start the new topic, Bloch equation. Felix Bloch, the inventor of this technique, in fact, Felix Bloch actually acknowledges Gorter, who did the first experiment. This is, he got the idea from there and things like that. He does acknowledge that when they discuss that. Felix Bloch and Purcell. They got the Nobel Prize in 1952. Felix Bloch and Purcell, they were working in two different labs. Felix Bloch was working in Stanford, Purcell was working in MIT. And they worked independently. Felix Bloch was looking more from the precessional point of view in a classical, pseudo-classical picture. Purcell was looking at the energy level diagram. So eventually they converged and said, okay, that is the same phenomenon. But Felix Bloch has many more contributions. He actually came here also several times. He gave lectures here on several occasions. So he wrote phenomenological equations to describe this NMR phenomenon. Equations with macroscopic mechanization. Yeah. This is a vector, dm by dt, dm is a vector, is equal to gamma m cross h. H is the field. Some books use V as field, some books use H, so it doesn't matter, you have to be consistent with what you are using. M is the vector with components mx. Now these are numbers. When I say mx, my, mz. So when you write this, these are now numbers. Okay, this is a vector, so it has these three components. H is the total magnetic field. Let me, this is 1.81, this is 1.82. And H is your field H0 plus H1 e to the minus I omega t. This is your RF field. This is the RF and this is your Zeeman field, DC field. So I can write, this also is a kind of a vector, except that it is a time dependence over there. Okay. So this also I can write as hx, hy, hz. So with components hx, hy, and hz. So what will be dm by dt Okay, no. So let's write this explicitly now. D by dt of I mx plus j my plus k mz. What are the ijk? Unit vectors along the xyz directions. This is gamma space to write here. Let me write it down. Is equal to gamma I mx plus j my plus k mz cross I hx plus j hy k hz. So you can write it in the form of a determinant I, j, k, mx, my, z, hx, hy, etc. Again.
Sir?
Yeah.
So d and dt equal to gamma into m cross h. That itself is a Bloch equation.
Is a Bloch equation. That's the Bloch equation. Good job expanding that now. Simplifying that. So, and this is dmx by dt. Now we can write in terms of the components from here is equal to gamma my h naught plus okay, now I have to explain a little here. What is hx? So we choose hx is equal to h1 cosine omega t and hy is equal to minus h1 sine omega t. h1 sine omega t
that H0?
and h0 is here, no? h0 my h0. So I am expanding that determinant. See, my x xz is h0. Okay.
Oh.
Xz is h0. Because along the z-axis you only have the h0 field. And dmy by dt, actually these chalks are so terrible, they destroy the board. So this generates scratches because so hard. Gamma mz h1 cosine omega t minus mx h0 and dmz by dt is gamma minus mx h1 sine omega t minus h1 cosine omega t. Okay, so all these equations equals to number one after the other. This one is now 1.86.
Is H
Did I miss something?
In the first equation, there will be
H1.
Oh, yeah.
and HY is minus I H1 sin omega
And Z
HY
it is h1 here.
H1 here.
Huh?
And on the left, HY equals to minus I H1 sin omega.
Minus I h1 sine omega.
And then why not there? I mean, in those equations.
Where? So you get a minus sign, no? When you take the
Yeah.
J,
But
I should be there. 1 minute. Minus h1 sine, no, I is not there. We are just saying hy is, there is no I, sorry. There is no I here. h1 sine omega. Is that okay?
yeah.
Now you notice here, the relaxation is not included. In this equation, relaxation is not included. Okay, but so therefore you will have to modify these equations to include relaxation. So he did modify these equations to include relaxation. What I will do, I will simply write the modifications here itself. If we include relaxation, dmx by dt, this is minus mx by t2. I will tell you what this is. t2 okay, now this equation becomes 1.87. And for my, also he did minus my by t2. This is 1.88. And this will be, you have add this term minus mz minus m naught by t1. And this is 1.89. See, he introduced this is understandable. Of course, this we have gone through. Right? The Z magnetization is dependent on the spin relaxed structure time because it changes the populations. The populations are brought back by spin lattice relaxation time. What about these? We have there the mx and the my. These are the transverse components of the magnetization. Transverse components, they don't necessarily decay with the same rate as the longitudinal magnetization. We are now therefore two types of magnetizations. One is magnetization in the transverse plane, which is mx and my, and other one is the magnetization in the along the z-axis, which is also called as longitudinal magnetization. That relaxes by T1, spin lattice relaxation time, and that for the transverse relaxation, he introduced another relaxation time called as T2. It's called as spin relaxation time. How the two things are different, whether they originate differently, we will explain that. We will.
Why MZ will relax?
MZ is deviated from equilibrium. This is M0 is equilibrium magnetization along the z-axis. Okay, MZ is at any point in time, if the magnetization is different from M0, it will tend to go there.
No, usually it was M0 along XYZ.
No. Along the z-axis, it is M0. At equilibrium, along z-axis, it is M0. At equilibrium, in the transverse plane, there is nothing. It is 0. X magnetization or the Y magnetization in the transfer plane, there is nothing. And therefore, you don't find this minus over there. Anything that is created is extra. In the transverse plane, if you have a My magnetization, it is already non-equilibrium. At equilibrium, you don't have mx or my. Whereas along the z-axis at equilibrium you have m0, but you can deviate from equilibrium and then you have the mz. We call that as mz. So whatever is the deviation from equilibrium, that is what will enter here. N minus N naught. We saw earlier, right? Population difference. So in this case, there is no, in the transverse plane, there is no mx or my at equilibrium. Okay, so now there is a time dependence here. Therefore, clearly you can see all these components are time dependent. Mx, My, Mz, all of these are time dependent. This is because of the RF. Okay. Now to solve these equations, you use a trick. Let me also say that here T2 is a new parameter which is called as spin relaxation time. We want to get around this time dependence. It's not easy to solve when you have such a time dependent problems. So we want to get rid of this time dependence. So what should we do? To get rid of the time dependence, what should we do? No, that is a particular case, but you want to get rid of the time dependence. We did this earlier, if you remember. We have discussed this earlier. How to get over the time dependence. What are you looking at? You are looking at the evolution of the magnetization. Right? M is the magnetization. You are looking at the evolution of the magnetization as a function of time. Essentially, in other words, you are looking at the spins as they are moving. Now we want to make them stationary. In other words, we want to remove the time dependence. What should we do? Rotating frame. We go into the rotating frame. Make a transformation into the rotating frame. Transform these equations into the rotating frame, then you will get rid of the time dependence. After that, it becomes easier to solve the equations. So, how do we make this transformation? Into the rotating frame. Okay, I will only give you the transformation, but solution we will see next time. Okay, how? Yeah, there a question? No. We make this transformation. We define these entities. Two other components of magnetization. These represent now magnetizations in the rotating frame. So the U is the component of magnetization in the rotating frame along the RF axis. Rotating frame means you sit on the RF, no? That's what is the rotating frame. Sit over the RF, that's why you are stationary there. So we call U as mx cosine omega t minus sine omega t.
So, explain this U once.
So U is, this is the variable change. This happens because we are going into the rotation. This is a similarity transformation. Coordinate transformation, what do? You go from one frame of coordinates to another frame of coordinates. There is the similarity transformation. This is just that only. See, coordinate transformation. You must have done coordinate transformation. This is coordinate transformation, nothing more than that.
So this is a separate coordinate you're defining.
Separate coordinate, yes, exactly.
So U is along X.
U is along X in the rotating frame. So there is the new X, or you call it X prime, and then you have the Y prime. So U is along the X prime, Y is along, V is along Y. So this is V minus mx sine omega t minus my cosine omega t. And the inverse of that will be mx is equal to u cosine omega t minus v sine omega t, and my is minus u sine omega t minus v cosine omega t. Okay, so these equations, all these equations we put as 1 point. Okay, I think we can stop here. The solutions we will take it up next time.